So we'll be handling exact equation, which is the third form of solving differential equation. So exact equation, it can be expressed in the form of the m x y dx plus n x y dy, whereby we check for exactness before solving. So how do we check for exactness? The partial derivative of x over x y over the partial derivative of y must be equal to this partial derivative of n x y over x, sorry, whereby this the partial derivative of m and the partial derivative of m must be equal. And we are going to use the exact equation to solve. Here's problem 1, 2, and 3. So let's start with problem 1. Here's problem 1. So the first step, you need to multiply through by the x. By multiplying through by the x, we obtain multiply through by the x. Multiply through by the x, we obtain 2 2x plus y dx plus 2y dy is equals to 0. So you compare it with the differential with the exact equation format, which is mxy equals to 2x plus y. Then your n is equals ny is equals to 2. So our second step, we are going to check for exactness. If the equation is exact, testing or checking or testing for exactness of the equation. So how do we check for exactness? We remember the differential equation, which is the partial derivative of n over xy over the partial derivative of y equals to the partial derivative of n. It can be uppercase later, it can be lowercase later. Over the partial derivative of n, where this is your m and this is your n. So we solve partial derivative of 2x plus y into the y equals to the partial derivative of 2y over 2x. If you differentiate this one, you obtain 1. And if you also differentiate this one with respect to s, if you differentiate 2x plus y with respect to y, it will just be 1 because of this one. This will be 0. Then if you partially differentiate x with respect to y, since there's no y in this equation here, so it will be 0. So we can't solve since the m and the n are not equal. So we can't use the exact equation to solve this problem. So we'll move on to problem 2. So here's the problem. So we solve using exact equation. So our first step is to multiply the x through. So by multiplying the x through this equation, we obtain cos y dx minus sine xy. So we compare we compare this equation to the differential equation form, and we call m x y m as a function of x and y dx plus n as a function of x and y equals to 0. This is the exact equation, and we can relate it using this. We can also relate it in this form, which is where your m as a function of x and y is cos y, and your n as a function of x and y is x cos y, x sine y, sorry. So we write it as m is equals to cos y, and your n, this is your m, sorry, equals to x sine y. So our second step is to check for exactness of the equation. So we further check for exactness or test is the same thing. Either you test or you check, it's the same thing. Testing slash checking for exactness. And can be given as x y over y equals to x y over x, where your m is m, which is m, which is over cos y over dy equals to the partial derivative of the integer x sine y. So if you differentiate the first term, you obtain minus sine y, and if you differentiate this one, you have minus sine y. That's the answer. So this is the differential equation. This is an exact equation, so we solve further over partial derivative equals to, and the partial derivative of x y, it can also be nxy. So in form of writing m as a function of x and y, we can easily write it as the partial differentiation of x and the partial differentiation of y, instead of writing it at this term. So our first step is divide the partial of the x is equals to, where your m is cos y, so you multiply through by the partial differentiation of the x, we obtain the y equals to cos y. So we introduce our integral sign to the equation. To this integral sign, we obtain f as a function of f and y equals to x cos y, x cos y. If you integrate cos y, we obtain x cos y. So you attach a constant with respect to y. So when you're integrating with respect with x, you add the constant with respect to y. So when you're integrating with respect to y, you add the constant with respect to x. So that's it for this one. So you do for the second one now, which is, so now we do the same thing for x. So we multiply through by the x, we obtain partial derivative of minus x sine y dx. So we introduce our integral sign, we obtain f equals to the integral of minus sine x y if here is the y, here is supposed to be the y, and here is the y. Yes, here is the y. So we integrate this one, we have x function of integrate this one, we have minus x open the bracket of minus cos x y. So we attach a constant, which is the constant of x, y. This one is the constant of y, so don't be confused. So we state the general solution to be f x y equals x cos y plus c x. So we compare the two answers, the answer for x, the answer for m, and the answer for y, which is this one, and the first answer, which is x cos y plus c, the function of y, plus this one, which is x cos y as a function of x. So we can easily cancel out the cos. We have f to c cos minus common over cx equals to 0. So our general solution for this differential equation, the general solution is f as a function of equals to x cos y. Answer. Okay, here's the third example using exact equation to solve, and we can easily apply separating variables to solve before using exact equation. So let's try and apply separating variables to solve this one first. By applying separating variables, we obtain 2y minus x dy equals to x plus y dx. So we have x plus y dx minus 2y minus x dy equals to 0. So we call our exact equation. So our exact equation is mx plus y dx plus nx plus y dy is equals to 0. We can relate it with this equation. where our m is equals to x plus y and our n is equals to minus 2y minus x dx dy. So we test our second method is to test for exactness. So we test for exactness of the equation. Testing slash checking for exactness of the equation. For exactness. So how can we check for exactness of the equation? Over x y dy is equals to partial derivative x y over x. So where your m is x plus y, we have x plus y, and our n is minus 2y minus x over x. So if you differentiate this equation, we have 0 plus 1. If you also differentiate this one, we have 0 plus 1. So it's an exact equation, so we can proceed. We can solve further. We apply the IVM boundary on the IVM condition. So we solve further. So let the partial derivative of x be equals to x, and also let f as a function of y be equals to nxy, or simply mean that this m now, let the x and the y, so we have the f over the x is equals to x plus y. So it's multiplied through by the x, we obtain x equals to x plus y, all in brackets the x. So we apply our integral form. We apply our integral form and we obtain as a function of x and y equals to x squared over 2 plus xy. This is for m. This is for m. So we do the same thing for n, which is the same step and the same procedure. So you have over the y is equals to your m, if you remember, your m is minus 2y plus x. So you multiply through by the y. We obtain the y equals to minus 2y plus x dy. So you introduce our integral sign equals to minus the integral sign minus 2y plus x y. So let's integrate this stuff. We have x y equals to, integrating this stuff, we have minus 2y squared over 2. Let the 2 be cancelled out, plus xy plus cx. So we compare the two results for the form for x. We compare these two results for m and y. So we have x squared over 2 plus xy plus cy equals to minus squared plus xy plus cx. So these two can cancel out. We have our c of y, the constant of y, minus the constant of x, minus the constant of x to be equals to minus, let me write this thing well, let me bring it down. So the constant of y minus the constant of x equals to minus y squared minus x squared over 2. So our y, the constant of y to be minus y squared and the constant of x to be x squared over 2. So henceforth, our general solution equals to f as a function of x and y equals to x squared, the xy first, xy minus y squared plus x squared over 2. And remember, from the question, we have an IVP, which is initial value problem. And what's our initial value problem? Let's continue. So applying So we applying the IVM, which is initial value problem. In our first class, we discussed about that value problem to this equation. So let k equals to the function of x and y, and this is our initial problem equals to 1, where x is equals to 0 and y is equals to 1. So we substitute it into this equation. So our f as a function of x and y, select to be k, so it will be k equals to our x is 0 and our y is 1 minus our y is 1 squared plus 0 squared over, or in parentheses, over 2. So if we resolve this, we have k equals to -1. So therefore, -1 equals to xy minus y squared plus x squared over 2. By rewriting this equation, we get xy minus y squared plus x squared over 2 minus 1 equals to 0. Here's the final answer.